Welcome, everybody. This is November 23rd, and I'm Toby Delbruck, and I'm going to give you a lecture and show you some blackboard sketching, chicken scratching, as it's called, about photosensors, how it works in the eye, how it works in your camera, and show you something about the circuits that you'll study in simulation now for your exercise. So, the links to this 08 Photosensors 1 and 09 Photosensors 2 slides are already shared on OLED on our schedules page. And this week, the exercise you're going to do is actually a Python notebook, which is in our coach labs, lab 10 photo, group number, first name, lab 10 photo. And it's a Python notebook, but unlike the Jupyter Hub system that you're using for the coach chip, the class chip, we're not going to use the class chip because it's not convenient to supply an optical stimulus to the chip remotely and to share that kind of setup. So this exercise is going to be, unlike the other one, it's going to be purely a simulation and analysis exercise in Python notebook. And I think it'll be quite fun for you because you're going to basically write your own SPICE simulation of the circuits and run this transient simulation, study how the circuit parameters affect it. And then you'll do a small signal analysis and look at the transfer functions as a function of frequency and look at the root locus plot. How do the poles of the transfer function move around as you change the circuit parameters? And if you look at it, if you study it carefully, you'll learn a lot actually about amplifier design and the design of transimpedance circuits. So the first part of the lecture here is about phototransduction, the visual pathway, the retina, and photoreceptors. Actually, before that, I'll tell you about the circuits. And then in slides, I'll tell you about silicon photosensors and about how you measure light with radiometry and photometry, about the photoelectric effect that makes electron hole pairs from light, about the absorption of light by silicon. There might be something that's not obvious to you about how light is absorbed by silicon as a function of the wavelength. And it's important to understand that if you're ever going to design a vision sensor. And then we'll talk about photodetectors, the PN junction, and how that collects charge that is created by shining light, and a little bit about quantum efficiency and spectral response, and then some practical stuff about so-called dark current. Dark current is a current that flows in a photodiode even when you're not shining light on it. And it's the main limitation to making things work under low light conditions. And then I'll show you how to estimate the actual photocurrent you get in a photodiode on a chip if you know that the scene is illuminated by a certain number of lux, which is typical for some condition. Like, for example, I can know that your living room at night under soft lighting is going to be about 50 lux on it. If you go out in the beach in bright sunlight, it'll be 100,000 lux. If you're under moonlight, full moon, that's 0.1 lux. I just know these numbers because I've been working a long time. But once you know how much light is falling on the scene, and you know the reflectance of the scene, and you know what kind of lens you're using, you can estimate how much photocurrent you'll actually get in a photodiode on a chip. And it's important to know that in order to ensure that your circuit will work. And I also have some slides about one slide about how your 3-transistor smartphone pixel works, that uses a very cool structure called pin photodiode and correlated double sampling. And finally, the exercise will be about logarithmic photoreceptors, which is the front end of many of the neuromorphic chips, including the DVS dynamic vision sensor event camera. And so in the exercise, you'll study two different circuits, a source follower, which is kind of a passive logarithmic photoreceptor, and a transimpedance feedback arrangement for this logarithmic photoreceptors. And we'll go through the computation of the DC response. And in the exercise, you're going to do a transient large signal response simulation using the solver, the time-stepping Euler solver within NumPy. And you'll also plot some small AC small signal analysis for the circuit. So are there any questions? If there are any questions, by the way, please ask them during this lecture. Okay, just interrupt me by turning on your microphone because I can't see your actual chat. I think there's a couple of chat. Oh, right. You can download if you want. There's an item that's, if you want, you can install Anaconda or even better, Miniconda, and that comes with the Jupyter server. But that does mean you have to install stuff on your PC. And, it doesn't always go perfectly smoothly, despite what people say. Remember, very important to use Python 3.7 and larger. Don't use Python 2 anymore. Okay. So like I say, interrupt me if there's any questions. Okay, so the exercise you're actually going to do is on these two circuits. The one is a source follower photoreceptor, and the other one is a transimpedance log photoreceptor. And to understand how these things work, you have to understand that when you shine light on this photodiode, it creates a current that's basically just proportional linearly to the light. If there's no light shining at all, there's going to be some dark current, right? But as long as you have enough light that's a few times the dark current, this current flowing down here acts pretty much like a constant current sink that's proportional to the light intensity. Now, what happens if you just put a transistor on top of it and, for example, tie this gate up to some bias voltage or even to VDD? Can you see what happens? Basically, this photodiode is now forcing a current, just like in a source follower, where you have a bias transistor here. Now you have this photodiode. And it should be pretty clear that if you don't move the gate voltage, then if you increase the current, what happens to the source voltage? If I increase the current here, well, if I increase the current, the source has to go down, right? Because you need a bigger VGS to supply that same current. And since the current flowing through this transistor is exponential in the gate source voltage, then it follows that the voltage is logarithmic in the current, right? It goes down, the voltage goes down as the photocurrent goes up. And every photodiode has an associated parasitic capacitance. That's why you put a capacitor here. And that, of course, low pass filters the output signal. Now, it should be obvious to you now that you've thought about these subthreshold transistors for a while, that there's a time constant associated with this node, right? And the time constant is related to this capacitance and the conductance of this node. In other words, how much does the current in this node change when you change the voltage? So what's the conductance of this node here? Well, I just told you that the photodiode is basically like a constant current sink. That means that the current here doesn't hardly at all depend on the voltage. But what about the current in the top transistor? Does it depend on the voltage? Yeah, definitely, because the source voltage heavily controls the current, right? Remember, it's e to the kappa VG minus VS over UT, and the exponential of that, that's the current. So the current here is exponentially dependent on the source voltage. But you can compute the effective conductance at any particular operating point. That's just the source conductance of this subthreshold transistor. And remember, in subthreshold, the source conductance of a transistor is just exactly the current divided by the thermal voltage. Okay, so the time constant associated with this node is C times R, or C over G, and G is the current divided by the thermal voltage. So the time constant of this node is really simple. It's just, I'll write it here. If I can annotate. By the way, if you guys have any questions, please ask me, okay? Let's just try this line. Yeah, so what's the tau here? Tau equals C over G, which equals C over I, where I is this current, times UT. So that's really nice. C times V is a charge, and I is a charge per unit time. So it works out that this is seconds. You know, if you have charge per unit time divided by, if you have charge divided by charge per unit time, then the time goes on top. All right, so it's clear that the time constant is inversely proportional to the photocurrent, right? In other words, the brighter you shine light on it, the faster the circuit gets. That's what you get when you have a logarithmic photoreceptor, because the conductances are proportional to the currents. Okay, so that's a perfectly fine photosensor. It has some problems, though. Does anybody want to remark what some of the problems are? So what about the output conductance of this device? Well, the output conductance, in other words, how hard it can, how strongly it can drive a load, is just, the output conductance is just this same GS, right? The GS looking up into this transistor. So if I make the current really small, it's going to be really, really weak. Yeah. In other words, the lower the current, the weaker it is to drive something downstream, like some capacitive load. So that's one problem. Also, it could be really slow. If you actually work out what the level of current is in this photodiode, it's going to be tiny under many realistic light conditions, like from living room light on down to moonlight and starlight. It'll be really slow. So to deal with that, we go to the arrangement on the right, which is this transimpedance log photoreceptor. And let's try to understand how that works. So let's suppose, you see, it's just the same thing, but now instead of tying this gate voltage to a fixed voltage, we actually take the voltage on the photodiode, invert it with this inverting amplifier, and then feed it back to the gate. And so now let's suppose that the photocurrent here increases. What happens to this voltage on the source of this transistor? If the photocurrent increases, the voltage goes down, right? Just like before, because we're pulling more current out. So that makes this voltage go down. And what happens to this voltage here at the output? Does it go down or up? I mean, if I turn this, yeah, it goes up, right? So if I turn off the bottom gate of the right transistor, the output voltage must go up, right? Because less current is being sunk, right? So this will go up a lot, actually, because remember, this is the voltage amplifier. So this will go up a lot. And that's the gate of the feedback transistor. So now what happens is that if the current increases, what happens? The source doesn't change. It's fixed at a virtual ground, and the gate goes up. See, before the source went down, and now the gate goes up. And now that looks like it's doing, it basically has the same voltage gain. If you change the current, the voltage gain is the same, but the big advantage is now you have an independent power supply through this bias transistor, which just acts like a current source. And now the output impedance is set by the amount of current IB that you bias that transistor by. And so now it can drive an arbitrary load just by turning up IB. But there's another big advantage too. Do you see what it is? If I put a capacitor here, what happens? This is the parasitic capacitor associated with this photodiode. So I have a time constant there, a C over G tau time constant. But what is the G now? Before, the G was the source conductance. But what's the associated conductance of this node on the photodiode now? Well, the conductance is how much the current in this top transistor here changes when I change the source voltage here. Right? But do you see how it's amplified now? Because now when I pull the source voltage down a little bit, the gate voltage goes up 100 times as much if the voltage gain is 100. And so if the gate goes up when the source goes down, that effectively increases the conductance by a factor of 100. And so the tau, which is the C over G, is 100 times is about, say, if the gain here is at like 100 minus 100, then the tau will be C over G of the left circuit divided by 100. Which is the gain of the amplifier. Because of the effective conductance of that feedback element, it's much, much larger. So it's also, not only can it drive a load, but it also is many times larger. That's a really cool idea. That's why it's called a transimpedance amplifier, because you kind of move the impedance away from the input node and put it back in a feedback loop. Does everybody follow that?
So what I was asking is it possible to have this high gain with a single transistor arrangement that we have here?
Yeah, sure. You could have this high gain. You mean with these two transistors on the right here, these blue transistors? Is it possible to get a gain of 100? Sure, it's possible. You might have to make them longer than minimum length. Okay. Now there's something I'm not telling you about, and I'm not going to say much more about it in this lecture because it's a little bit. At least I'll say more about it possibly next week. But you have to realize that there is something I'm leaving out of the story, and I'll give you a hint to it. What if you have a parasitic capacitance here and here, and you do have those parasitic capacitances because they're the gate to drain or gate to source overlap capacitances. They're physically this little overlap here between the gate and the drain. those little yellow capacitors. What happens if you have those?
Get multiplied.
Yeah. Then it turns out that these little tiny parasitic capacitors are amplified also by the gain of the amplifier, right? Because now when I move the input node down 1 millivolt, say, you see the yellow arrow here, then the output node goes up 100 millivolts. And so this capacitance value is multiplied by a factor of 100 with respect to the input, which must charge it. So it makes those little tiny parasitic capacitors look much larger than they actually are because of the voltage gain of the amplifier. And that gets rid of a lot of the speed up, because the more gain you put on the amplifier, the more it amplifies that parasitic capacitance. And so it doesn't speed up as much as you would like. And that's something we'll maybe speak about a bit more next week. But anyway, this is enough. These two circuits are the ones that you're going to analyze for your exercise. And the exercise this week is going to go over 2 weeks. So you're going to spend 2 hours this week, and then next week, another 2 hours. And the first exercise session is going to be Thursday, the usual time, Thursday afternoon this week, in 2 blocks of each 2 hours. Is that clear?
I just have one more question about the schematic, if I can ask real quick. So the reason, because on the left-hand side, the source voltage goes down, the gate voltage goes down for the right-hand transistor.
Well, goes up. The right-hand side, the gate voltage goes up. The source goes down, but the gate goes up because this amplifier is an inverting amplifier. It's a negative gain.
Wait, but how come if the source on the left-hand side goes down, how can the gate for the right-hand bottom one go up if it's the same part of the circuit?
Yeah, I didn't label this very well. Let me try to label it. Like, let's call this V1,
Okay.
V2, and V3. Okay, now,
Yeah.
which are you speaking about?
No, I'm speaking about the source voltage. So V2 is the source voltage of the left-hand transistor,
M1?
and M1, and the gate voltage of the right-hand transistor, right?
Yeah.
So yeah, I guess my only question was, if the gate goes down, so DS for M2 goes up because we're providing a bias current with M3, right?
Yeah.
Yeah, okay, just needed to know that. Thank you.
Sure, no problem. Now, the gain of this amplifier on the right, I'm going to tell you this because you need to know it for your exercise. What determines the voltage gain of this amplifier? Remember, in the very beginning of the course, I explained the concept of intrinsic voltage gain, that transistors have a kind of intrinsic voltage gain. For the purpose of the exercise, you're going to have an ideal current source IB. Ideal. That means there's no, it has no drain conductance. It's always exactly IB that's pushing out mathematically, right? But in your simulation, you're going to introduce an early voltage into this transistor here, GD, which is equal to the saturation current divided by the early voltage. Okay. Otherwise, it mathematically doesn't work. You can't have 2 perfect current sources with different currents fighting it out. The voltage, you can't find a solution for that because they're not compatible. Yeah.
Could you repeat the last part? Because a sound went off when you started drawing the purple things.
I couldn't understand you. Was that
the sound went off when you started drawing with the purple color for a few seconds?
Oh, I see. So you have to, can you hear me now?
I can.
Okay. Okay. So you have a perfect current source on the top right, IB, right? That's an ideal current source. It just sources IB, period. In order to turn these 2 transistors into a voltage amplifier, the bottom transistor must have a finite drain conductance, GD. And GD is determined by the early effect to be ID over the early voltage. It's a current divided by the early voltage. It's the drain current. So then you will remember that the voltage gain of such an amplifier is equal to the transconductance GM divided by the drain conductance GD. Okay, and you remember you calculated that early in the course, right? GM divided by GD is kappa. Let's see, what's the kappa I B over UT? That's the transconductance, and the GD is ID over VE. And so from that, I'll just go over here. The gain here was VE kappa over UT. Remember this, you had an exercise, or at least I showed you in the lecture, that the gain of the intrinsic voltage gain of such an amplifier is determined by the ratio of the early voltage to the thermal voltage when the thing's running in sub-threshold.
Could I ask a question? Sorry.
Yeah.
Is M3 a pFET to create the inverting amplifier? Sorry.
You need a current source at the top. You need some stiff current source, right? And it needs to supply a constant current, a rather stiff constant current. I mean, it'll have a finite conductance. I'm just simplifying it here, saying the only thing that has a conductance is the M2 transistor.
Oh, sorry, my question was, is M3 also an NFET? Shouldn't it be a pFET to create the inverting amplifier?
Thank you. Yes, thank you very much. You're absolutely correct. No wonder people were confused. I made a mistake in the picture. Let me draw this with the proper color here. This should be like this. Thank you for pointing that. That's a pFET, obviously. Yeah, you could have had an inverting amplifier, but it would have had very, very low gain, only unity gain, right? Like a source follower. If that was an NFET, it would be an inverting amplifier, but it'd be a very crappy one. Thank you for pointing that out. Now, I hope it makes more sense now this way. Okay, so that's what the exercise is going to be about. And you can come back. I'm going to do some more analysis of these circuits later on. But let's just go and talk about how vision works in the eye for now.
I think the notes you labeled on the left and right, I think is a bit confusing because the V1 is supposed V1 and it should be also V1, right? On the right side picture, because you labeled it as V2.
Well, I just give different names here. Yeah, I just say V1, V2, and V3 to make them all completely separate. This should be V3. It's really, you're right, it corresponds to V1. It corresponds to V1, that's correct. But for the purpose of this picture, I just named them V1, V2, and V3 because they're separate electrical nodes. Is it clear?
Yeah.
Okay. Okay, let me attempt to focus here again. I have to stop the drawing tool. I think I'm going to have to, sorry guys, so pitiful. If you look at the bottom of the view of your brain, this is like looking up through your brain, through your spinal cord here, and you look up at the bottom here, you know, what we're looking at here, these frontal lobes here are kind of like next to your eyes, actually. They're sitting on top of your mouth and your nose area and stuff. And then from the visual cortex, which is at the back, or actually starting at the eyes here, you have these optic nerve. Each of these optic nerves has about 1 million nerve fibers in it. And then they cross over in a very interesting way that I won't go into, but half of the nerve fibers go to one half of the brain and the other half go to the other half at the optic chiasm. But then these the ganglion cells, these ganglion cells coming from the eye, they terminate actually in the lateral geniculate nucleus. It's part of the thalamus. It's part of the ancient midbrain, the reptilian kind of part of your brain. And from there, there's some processing going on that's still not very clearly understood, but there's like 6 layers of processing there, or even 8, if you count some new ones that people have discovered recently. Anyway, then about 100 times as many fibers come out of the lateral geniculate nucleus and they go back to the primary visual cortex, which is sitting right on the back of your head. That's the first visual area that has the most low-level processing in visual cortex. People see receptive fields in primary visual cortex that are responsive to edges, moving edges, patterns and stuff like that. But it's a huge area of cortex. I mean, the whole cortex, if you take the whole cortex and could flatten it, it'd be about the size of a large pizza. And the primary visual area is maybe about total area like this, a lot of cortical real estate. And so that's how visual processing starts in the brain. But then if we look back at the eye, we see that it's actually an amazing structure that has, you know, a lot of sophistication all by itself. So it starts with the optics. So there's a cornea, which is an optical focusing tissue here that the contact lens sits on the outside. And then that does most of the focusing, but then the accommodation, in other words, your ability to adjust the distance, which goes away by about age 50 or so. You can't change your focus distance anymore because this thing hardens up. Ultimately ends up creating a really sharp image of what's out there in the world on the sheet of retinal tissue at the back of the eye. This retinal tissue is about, I think, about 0.5 millimeter thick, and it has a consistency of like wet toilet paper. It's quite delicate because it's just neurons. And the neurons are stacked up so that the photoreceptors and light sensitive cells are sitting right against this pigment epithelium. This is where every night while you're sleeping, the photoreceptors replace their bleached out pigments. And there are rod and cone photoreceptors, and these run all in continuous time with a supply voltage of about 100 millivolts, biological supply voltage of 100 millivolts. And then they connect to horizontal cells and bipolar cells in the outer plexiform layer. And these bipolar cells are called bipolar because they have two tufts like this, one that tucks to the outer plexiform layer and the other one that tucks to the inner plexiform layer. And in the inner plexiform layer, there are dozens of classes of amacrine cells, which connect laterally between these bipolar cells and the ganglion cells. And there are also horizontal cells here that connect laterally in this outer plexiform layer. These horizontal cells seem to compute kind of a local spatiotemporal average of these photoreceptors. And then these bipolar cells seem to take a difference between the photoreceptor value and the local spatiotemporal average computed by the horizontal cells. So it gets a kind of a high pass filter here already. But there's much more complex processing happening here in this amacrine cell layer, which is just cartooned here. Anyway, finally, these amacrine cells are talking to the bipolar cell. Well, the ganglion cells, which are these cells here, finally send spikes out over the optic nerve to the thalamus. And that's how you're seeing the screen right now, through those spikes coming over your optic nerve. So this is a super simplified picture of what's really going on. And the retinal biologists have been working on this, understanding what's going on in the retina, which is highly complicated, for decades. And here's another cartoon that again shows the cones and rods, horizontal cell, bipolar cell, and ganglion cells, all these things. You can have a look at this later. I want to show you what the real biology looks like later. But I'll just tell you that there are two kinds of photoreceptors, rods and cones. Most of the photoreceptors in your eye are actually rods. You have like 126 million of them in each eye. They're sensitive in dim light, the lowest 3 decades of light sensation, from like dark, a starlit night to, moonlight and a little bit above moonlight. And they saturate at high illumination. And there's one light sensitive pigment in blue-green. And they're not present in the fovea. Right. So you all have been, if you've been camping and you want to see a faint star, you have to look a little bit away from it so that the rods can pick it up. Otherwise, you don't see it. Because the other photoreceptors you have in your eye, which there's only 6 million of them, are cones. They're sensitive to the upper 9 decades of light intensity, and you have different color pigments that give you color vision. In fact, here is the photoreceptor spectral sensitivity for the different kinds of rods. Actually, this is misplaced. This is the rod sensitivity. It's in the blue-green. And then there's the short, middle, and long wavelength pigments for the cone photoreceptors. Now, let's talk about the spectrum of electromagnetic radiation and where does visible light fit into that. I'm sure many people here have seen this picture, but if you look at the energy of a photon in electron volts, we're kind of lucky in a way that visible light is around 1 to 3 electron volts. These visible photons that we see the world with are from 1 to 3 electron volts of energy. In fact, a green photon is a good rule of thumb that it's about 2 electron volts. And within that spectrum, of course, the light goes from red, which is low energy, up to purple, which is the highest energy. And the wavelength of those photons goes from 400 nanometer, that's like the deepest purple that you can see, out to about 700 nanometers, which is like the deepest red that you can see, right? Actually, it goes past that in the near infrared that silicons can still see, but you can't see it, like how TV remote controls work. But now let's look back at the photoreceptors again. So they're actually distributed. If you look out in the outer retina, in the peripheral retina, right, where you have mostly rods, you'll see big areas where there's no cones at all. And you see these rods that are tightly packed like this in a hexagonal lattice. And if you look in an area that does have cones, like closer to the fovea, you'll see a bunch of rods again, and then much bigger cones like this. And this is a very cool plot of the distribution of those photoreceptors in the eye as a function of angular eccentricity from the fovea. So this is the number of receptors per square millimeter. You can see that the cone density peaks right in the very middle of the fovea, and then it drops off to a rather constant low density. But the rod density is very low in the fovea. It rises up to a peak, and then as you go more and more to the periphery, the rods get bigger and bigger. So they're sensitive to lower and lower light intensity. It's a cool distribution because, nobody builds an image sensor like this in a circular shape, right? So it's a very cool technology for vision. But we'll talk more about this next week, but I just want to tell you some things about the beautiful biochemical amplifier of the photoreceptor. And so if you look at a photoreceptor like this, a biological photoreceptor, it consists of an outer segment and an inner segment. Then it has a kind of a connecting thing, and then the cell nucleus where the protein is synthesized and stuff like that. And then you have a connection at this synapse here to the horizontal cells and bipolar cells. And so the outer segments are actually modified cilia from bacteria with discs filled with opsin, the molecule that absorbs photon as well as voltage-gated sodium channels. So within each of these rod photoreceptors are hundreds of these kind of flat discs of lipid bilayer, and floating around in this two-dimensional disc, actually floating around and diffusing around two-dimensionally, are these structures that holds these opsins, which are the things that absorb the light, and then cause a whole reaction, a whole chain reaction of biochemical processes that end up closing sodium channels in this outer membrane. And ultimately, when you flash this light onto this thing, it'll end up within a few milliseconds of creating a voltage change over here, which changes the release of neurotransmitter at the terminal down here. So this protein opsin contains this pigment called retinal. In rods, the opsin plus retinal together are called rhodopsin. In cones, there are different types of opsins that are color sensitive. Okay, so here's what it actually looks like. So when a photon is absorbed by a rod cone pigment, the retinal undergoes a photoisomerization to all trans retinal, which changes the conformation. And this conformation change triggers a biochemical cascade that causes hyperpolarization of the cell and a decrease of glutamate release at the synapse. And so here's what it looks like as a function of time in milliseconds. This is the photocurrent, the actual current across the membrane of this cell that's extracted like from a turtle retina as a function of time for a rod and for a cone in response to the flash of light. You see how the rod responds to this flash of light? So this is different levels. This is different intensity of flash. Just a little flash that causes one single rhodopsin event. It causes a change in the current of maybe a few picoamps. Right? It gets bigger. And the bigger the flash of light, the longer it lasts. Cone's very different, right? It looks like a high pass photo. You make a flash, responds, and then it rebounds back the other direction, and then it goes back to zero. Whole thing is over in about 200 milliseconds. This is slower than what happens in us because it's from a cold-blooded animal, not running at body temperature. So like, I think these famous experiments from Baylor or from turtle retina. Okay, so this is a cool plot, which I really love this plot. I use this a lot in my PhD work. It shows the peak potential reached by such a cell in millivolts as a function of log intensity of the light shined onto the cell. And there are actually two sets of curves. One curve, this flat one here, is the steady state response. So this is log intensity here. What it shows is that the DC voltage across the cell membrane is logarithmic with the light intensity. Each step here is 1 decade of light intensity. So it's just a logarithmic photoreceptor. So that, assuming that the that the neurotransmitter release is somehow related monotonically to the voltage, then it shows that it's just in DC, it's just a plain log photoreceptor. Very beautiful thing is that if you suddenly change the light intensity around some operating point, like suppose you sit here at -2 decades log intensity, then now you suddenly change the photocurrent. You change the amount of light. What happens is the membrane voltage actually sweeps along this curve. This is for rapid changes, faster than a hertz or so. If you now leave the light at a bright intensity, it'll eventually go back down to the flat curve. But now it's adapted around that point, and now it'll move around that new operating point. So it's like a little bit like a bandpass filter, has a higher gain for changes than for DC. You see why that makes sense to do that? Because it makes you sensitive to small changes around some operating point. And so we know how to build photoreceptors like that. In fact, some way the DPS is a little bit like that, because it always adapts itself and memorizes the most recent intensity. All right, so now let me tell you a little bit about radiometry and photometry. So radiometry is about measuring light energy in watts per square meter. And an ideal sensor has an equal sensitivity in all wavelengths of light, which is not reality. But the basic unit of light is watts measured by photon energy. And so the radiance coming from a surface is watts per meters squared. So it's like you take, the area of the thing that's radiating the light, it's watts per meter squared per steradian. And steradian is a unit of solid angle. It's like a fraction of the hemisphere. And then you have a measure called irradiance, which is how much light is falling on a surface. It's just watts per square meter. Simple, right? In fact, that's what the photometer in our lab measures. It'll just tell you that if you go in the office, it'll be about 2 watts per square meter falling on the office desk. Now, but that doesn't describe whether that light is visible or how visible it is, because your eye is definitely not sensitive to all photons with the same sensitivity. You're most sensitive to what wavelength of light, or what color of light is your eye most sensitive to? Does anybody want to take a guess?
Green?
Close. It's actually kind of yellow. And it explains why sodium lights that they light the street with at night, at least in the US, are very efficient, because they emit radiation exactly at the peak sensitivity of the eye. That's close. That's right. Okay, so and the sensitivity of your eye to light is described by photometry. Photometry means visible units. And in photometry, the spectral sensitivity of the sensor is matched to the average human eye with a peak at 555. That's the yellow of sodium. So the basic unit of photometry is a lumen. And so you describe such surface brightness. This is visible brightness by luminance. Like when you buy a computer screen, like a new monitor, it'll tell you what the luminance is in candela per square meter, which is actually lumens per steradian is 1 candela. So this is lumens per meter square per steradian. That's like a measure of brightness. And the other corresponding measure describes how much light is falling onto a surface is called illuminance, and that's measured in lux, which is lumens per square meter. And so when you describe how brightly illuminated a scene is, you describe it in illuminance in lux. You say, the scene was getting about a 1 kilolux. We were at 1 kilolux. And that'll tell everybody how brightly your scene was illuminated. Okay. You guys all with me so far? I'm sorry about the tedious slides, but I have to say these basic things. So the photoelectric effect is about how you make electron hole pairs with light. Let me look at the comment here. Yeah, candela. Yeah. Oh, that's right. Actually, candela is candle. So 1 candela of light is actually the light emitted by 1 candle. Actually, candles put out a very uniform amount of light. It's hard to make a really bright candle or a dim candle. Somehow about the physics of wax and the wick, basically there's only a candle of power. And if you want more light, you need more candles, right? More wicks burning. Anyway, So in quantum electronic phenomena, which electrons are emitted from many metals after absorption of energy from EM radiation, such a visible light. That's the photoelectric effect. And it was described by Hertz in 1887. And the effect takes place with photons of a few electron volts of energy. And the photon energy is actually the energy needed to remove an electron from its bound state, plus the kinetic energy left over in the electron. So like the higher the energy of the photon, you don't get more electrons, right? Unless they're really high energy. You just get a faster electron. I guess it gets shot away from the atom faster. So I guess you all know that light consists of EM radiation, and that the energy of a photon is Planck's constant times the frequency, or hc over lambda, where c is the speed of light. And the important thing that you should remember after this class is that a wavelength of 555 nanometer has a photon energy of about 2.1 electron volts. And that the reason that the 2.1 electron volt is valid because do you remember what the band gap of silicon is? Anybody want to type the band gap of silicon?
1.2.
Yeah, about 1.1 electron volts. So this has twice the band gap, right? A green photon. So it's clear that the photon must have at least the band gap in order to create intrinsic photoelectrons. If it doesn't have at least that band gap, it can't get an electron from the bound state into the conduction band. And so this shows this. Here's the valence band, here's the conduction band. If the photon has at least this band gap, which is 1.24 electron volts, depends a little bit on temperature, then it can make an electron hole pair. You can also make electron hole pairs from the so-called states that are in the middle of the band gap, but we won't talk about them because they're usually, that's something you don't want to happen. Okay, so this intrinsic photoelectric effect, the one normally used for sensors, consists of interband transitions. So with electrons elevated from valence to conduction band, that results in generation of electron hole pairs, and the maximum visible possible photon wavelength is 1.24 divided by the band gap. Actually, it's 1.24 electron volts, right? No, the wavelength. This is not correct, I think. 1.24 microns. Yeah, so the longest wavelength of photon that could actually make an electron hole pair is 1.24 microns. But we're going to talk about why it actually doesn't work with such a thing in a minute. Okay, yeah, so the longest possible wavelength is 1.1 microns. That's what I thought. Okay, so now, how does light actually get absorbed by silicon? So here I have light shining on a piece of silicon from the side here. And so assuming that it has at least that band gap of energy, it has a probability of making electron hole pairs as it passes through the silicon. And any one particular slice of silicon, it has some probability, right? And so it's just kind of random when that happens. And so as a result of that, the flux of photons goes down exponentially as you go into the silicon. In other words, the light gets dimmer exponentially as you go into the silicon. Is that kind of obvious? Because every slice removes some fraction, right? So it's kind of clear that it's a geometric reduction. Okay, but how does that vary with wavelength? In other words, would you expect a red photon with low energy or a blue photon with high energy to penetrate further into the silicon? Does anybody want to vote? Blue. You expect blue to penetrate further before it makes an electron hole pair. No, actually, that's wrong. Thank you for saying that anyway. So it turns out that the longer the wavelength of light, the lower the energy, the further it tends to go before it makes an electron hole pair. And if you remember the density of states business, you remember how when you have all these quantum mechanical states, the higher the energy, the more states there are. Turns out that's the dominant effect, right? The higher the energy, the more ways there are for it to make an electron hole pair. And so the shorter it goes before it makes it. And so that's encapsulated in this plot here, which I redrew from a famous paper where it was measured in bulk silicon. This is the, let me get this pointer out of the way. The bottom axis here, this is the wavelength of the light in microns. So you see green here is around 0.55 microns, right? Blue is around 450, 500, something like that. And red is around 700. And this is the so-called absorption length. That's the factor that when you go e to the minus x over L, it's like the exponential absorption length. And you see here within this visible range here, the absorption length in microns goes up as the wavelength gets bigger. In fact, it changes about one decade every 200 nanometers within that range. So a red photon, the absorption length is around, say, 3 microns, and a blue photon, the absorption length is around 0.2 microns. So blue light gets absorbed right at the surface. Red light can penetrate down. And what about infrared light? Its absorption length is like 30 microns. So it really penetrates deep into the silicon. So it's hard to capture deep infrared because the photodiode's right at the surface. And most of the light is actually absorbed deep in silicon. So you have to somehow make the silicon very, very pure so the electrons can diffuse up to the junction and get collected. Okay. So actually, it turns out there are different kinds of silicon photodetectors called photoconductors, photodiodes, phototransistors, and photogates. In practice, the only one that people really use is so-called photodiodes. So that's the only one I'm going to talk about today. Do you want me to draw this? I mean, I hate to show you this stuff with slides, but let me show it here, and then we'll go back to it. So you remember a p-n junction, right? So which side is p side here? So let's suppose that these circles here represent mobile carriers, right? So here you have lots of mobile holes, and here you have lots of mobile electrons. So this is the p side, right? And this is the n side. And remember, when they come together, it forms a space charge region. And within that space charge region, it's depleted. So there's essentially no mobile carriers compared to the neutral regions outside. But within that region, there's a very strong electric field that builds up to a peak in the middle and then goes back to zero on each edge. And that electric field is there to oppose the diffusion current. Remember, everywhere within this junction, the drift and diffusion have to balance each other. So what happens if a photon shines on here and it makes an electron hole pair? This electric field will rip the electron and hole apart and take them back home. Remember the one thing that I tried to teach you about that is that carriers go home. The electric field always pulls the carriers back home to their majority region. So the electric field here, which is opposing the diffusion of these holes, is pointing back to the whole region, right? So it'll pull the hole to the left and the electron to the right. So if you shine light right on the junction, it'll create electric current. Basically, 1 unit of charge for each photon that you can actually collect. Not 2 units, 1 unit. But what if you shine, and that's shown here by this band diagram at the bottom, you can look at later. So that's why the current is just basically linear with the light intensity. Now, what happens if you make an electron hole pair out here in the N region or the P region? Can it also make a photocurrent? It can. It turns out it may or may not actually get collected by the junction. And the way you can see that, if I can find this annotation bar, which I can't find anymore. Yeah, I don't know what happened to my annotation bar, disappeared. Anyway, I'll just point it here. If you make an electron hole pair within one of these neutral regions, like suppose you make it over here, right? So you're going to make an extra mobile electron here. These, by the way, this is a fixed charge, not a mobile. So if you make this extra electron, if I draw a circle around this, then what happens is it might come together with a hole and just recombine. Then you lose it. But because the diffusion length is very long, it's a good chance that it'll diffuse around randomly. And as soon as it gets to the edge of the depletion region here, the electric field will just rapidly shoot it across. So there's a region on each side of the depletion region, which is approximately the diffusion length of the minority carriers, that also collects charge in the photodiode. Okay, so it's not just the depletion region that collects charge. It's the area around the depletion region also collects charge. And so then you have these equations here for the reverse current and the responsivity that I won't go into. But the basic idea is that you get a current that's proportional to the light intensity. Now, in practice, this all is really nice. You can make a photodiode by just drawing a cross-section. You just draw an implant in the silicon like the N-well into a P substrate, and that makes a decent photodiode. The problem is that such photodiodes also leak in the dark. So this dark current limits the low light performance. And in a typical process, the junctions leak about 1 nanoamp per square centimeter of junction area for large area junctions at room temperature. And this leakage current actually corresponds to about moonlight scene illumination. So the basic photodiode that you get in a process is quite leaky. And it's because there's bad stuff that happens at the mid-band states, and especially where the junction comes up to the surface. In fact, this leakage is dominated by the edges of junctions where leakage is 10 to 100 times higher. So this little bit of red edge here leaks as much as this blue area in the middle of the junction. And also this dark current doubles every 6 to 8 degrees. From 25 to 60 degrees, it increases by a factor of 30. So that means when your camera gets hot and you're trying to run it at night, like in Las Vegas, or if you leave it in a hot car and suddenly bring it inside, it's going to work really crappy because it's leaking lots of current. People can do things like trying to anneal out mid-band states, hydrogen annealing, all kinds of steps. If you follow all these steps religiously, you can get photodiodes that are much less leaky. But you have to pay for that in a CMOS image sensor process. Okay, so the last thing I want to show you about this stuff is how you actually estimate photocurrent. So suppose I tell you that the scene your camera is going to look at has a scene illumination of 10 lux. How much light is going to shine onto your pixel? So a good rule of thumb is that 1 lux shining onto a surface is about 10,000 photons per square micron per second. And if you're interested, look at this beautiful book from Al Rose, who was at RCA and wrote this beautiful book about vision, human and electronic. I like this book so much that I scanned a bunch of pages from it, and you can get to them from the link there. So that 1 lux is, he gives this rule of thumb that a lux is about 10,000 photon per square micron per second, and moonlight is about 0.1 lux, office light is around 500 lux, and sunlight is around 100,000 lux. Also, a very interesting fact, at least to me, is that the average scene reflectance in the world is about 18%. And that was measured by Kodak many decades ago. So on the average, the world reflects about 20% of the photons that you shine onto it. And now you can compute, if you do some geometrical optics and stuff, you can compute that the lux that fall onto the chip, which is imaged with this lens with a certain F number, is 1 over 4 F squared, if you're looking at a white surface, right? F is the ratio of focal length to aperture. In other words, a fast lens have F 1.4. All the photographers know this stuff, right? About the focal length aperture, the aperture ratio of a lens. And if you assume that the quantum efficiency, in other words, the probability that a photon makes an electron is about 0.5, well, you don't have to assume that here. You can compute that the amount of light falling onto the chip in lux is the scene illumination times the scene reflectance times the quantum efficiency divided by 4F squared. And if you work that out, in a realistic scenario, you'll find out that the amount of light shining onto the chip is only a small fraction, say 1/30th or even 1/60th or 1/100th of the light falling onto the scene. So you have to take that into account when you're calculating such stuff. Okay. You guys all have a smartphone, right? So do you want to see how the smartphone pixel works? I'm going to show that to you now. Anybody know this stuff about the 3T pixel? So in your smartphone, your pixels usually have 3 transistors only. They're shown here: a transfer gate, a source follower gate, and a row select transistor. And in fact, even they have less than 3 transistors. Many smartphone pixels now have like 1.25 transistors per pixel. You might ask, how is it possible to have only a fraction of a transistor per pixel? Well, that's because they share this big source follower readout transistor here. So let me start at the beginning here. So if you look at a cross-section of the pixel on your smartphone, this is the surface of the silicon. Sitting on top of it is some color filter on each pixel. On top of that is a molded micro lens that focuses the light onto the photodiode. And now notice this. This is the surface of silicon. This is the photodiode here. It's an N photodiode sitting in a P substrate. It's actually called a buried photodiode because the junction never touches the surface. And the reason that junction never touches the surface is that's where you get all the dark current, right? Because you get these dangling states that are halfway between the valence and conduction band. That causes all kinds of bad dark current leakage. So to deal with that, they actually bury a photodiode down within the P substrate. Now this PN junction here still can collect photons, right? Because now it has a depletion region. And in fact, if you shine light on here, it'll make electron hole pairs. The electrons will stay in the N region, the holes will go to the P region, so you can make photocurrent here. But the only way you can get to this charge in this buried photodiode is through this transfer gate. And this transfer gate forms a channel of a transistor where you have on the other side this so-called floating diffusion, or FD. So this is just a normal NFET source drain. So the way this thing works is that you start by fully depleting this junction. In other words, you set this voltage on this N node at a high voltage, you turn on the transfer gate, and then you basically suck all the mobile charge out of this floating diffusion. So now there's zero mobile charge in it. So there's no noise because there's no mobile charge. It's just completely depleted. It's just like a complete depletion region. Now you turn off the transfer gate, and now this thing collects electrons. And when you're ready to read it, very cool trick here. This floating diffusion here is connected to the gate of a source follower readout transistor, which is then connected to a row select line transistor, which is connected to the column line. So when you want to read a row of these pixels, you turn on the row select. That connects the column lines to the pixels in this row. And now you read the voltage on this floating diffusion through the source follower. At the bottom of the column, there's a source follower load transistor. You read the voltage here. Now you turn on the transfer gate, and all the charge that is accumulated on this pin photodiode gets transferred over to this floating diffusion, and it changes the voltage on this gate. Now you read the new voltage. The difference of those two voltages is the proportional to the amount of light that's shined on the pixel. And that's what's happening in your smartphone pixel when you're taking pictures. You guys have any questions about that? Okay. It's all clear? I bet it's not clear, huh? But you can go back and look at it. You can ask me questions later. Okay, so the exercise this week is about logarithmic pixels. And so I'm going to tell you why this logarithmic response is useful. So if a photoreceptor has a logarithmic response to light intensity, then the scene illumination, I, appears in an additive term in the output, which is formed from the product of the scene illumination and scene reflectance. So the log of the product of the scene reflectance times the amount of light shining on the scene, I, is the sum of the logs, right? So this, presumably the scene illumination doesn't change. What's changing is the reflectance of the world, right? Because your camera is moving and looking at different parts of the scene. And so what your pixel sees is different reflective surfaces. And so differences between receptors over space or time leaves only the reflectance variations. So in other words, the change in this log of the scene illumination times the reflectance is just the change in the log of the reflectance. And so these reflectance variations are object properties, which are useful for vision. So the log is also very compressive, allowing a wide dynamic range operation within a power supply rail, as long as you can tolerate the transistor mismatch that you get in these circuits. Okay, so I showed you one of these simple log photoreceptors already. That was the source follower photoreceptor on the right here, right? But you could imagine other arrangements that are very similar to that. You can just put a diode connected transistor up here. It's very similar to this source follower thing. Now you just have a diode connected PFET, or you could stack up 2 diode connected PFETs. These are all passive, simple logarithmic photoreceptors that have the disadvantage that the output impedance changes with the light intensity and they're kind of slow and all that. And so now let's just go to the whiteboard for the rest of this stuff. You can look at the slides for all of it later, but I just prefer to work on the blackboard for this. Is that okay? Okay. So nobody had any questions about how that cell phone pixel worked? Is that clear? Okay. Okay, so let's do the analysis, small signal or large signal and small signal analysis of the source follower photoreceptor first. So let's take the photodiode like this. We'll put a load transistor on it. We'll just tie this to constant voltage VB. And this will be ground here. And so this thing has light shining on it, right? And it has a parasitic capacitance, which we'll discuss later. It has a V1 output. So how do we calculate the DC response of this thing? That's easy, right? If there's a light intensity I, which consists of a background, an IP, plus the dark current, ID. Then what do we know about this circuit? We know that e to the kappa, I'll just work in dimensionless units, e to the kappa times VB minus V1 equals I. Right? And so what we want to calculate is V1. So that's easy. It's equal to, so V1 is equal to, it's equal to kappa VB minus the natural log of I times UT. Well, there's no UT, right? Because we're dimensionless. So now if we want to change that back and put in the dimensions of stuff, the volts are okay. But we have to divide by some I0 here. Let me rewrite it here in this dimensionless, right? And when we add in back in UT and I0, it looks like this: V1 equals kappa VB minus UT natural log of I over I0. So let's plot now the log of the photocurrent IP on this axis and V1 on this axis. So what does that look like? Well, when it's bright, it's obviously going to go down with the slope of minus UT, right? But what happens when it gets dark? When it gets really dark, right, the photocurrent goes away, but what's left is the dark current. So you'd expect it to kind of flatten out. Simple, right? Okay. Shall we do the same DC analysis for the transimpedance photoreceptor next? Or would you rather do that or do the time domain response of this photoreceptor? So what do you prefer, that I write the differential equations of this photoreceptor as a function of time? Or would you rather go to the feedback transimpedance photoreceptor? Please give me your vote. Okay, so let's do the differential equation. So I'll go to a different color here. So I'll just write the ODE for this thing. It's simple. So what we want to know is the current flowing onto this capacitor here. C times V1 dot. That's the current flowing onto the capacitor. That must be the current, through the transistor minus the current through the photodiode. So that must be the current through the transistor. So it's E to the kappa VB minus V1 minus I. That's the whole differential equation. Right? The current flowing onto the capacitor, which is C dV dt, is equal to the current flowing in through the transistor, this top current, minus the current flowing out. That's the complete differential equation. Now, that's the large signal differential equation in dimensionless units. what we usually want to do is go small signal and express this around some operating point. And the way you do that is with you say the thing that the nodes have a particular conductance, a linearized conductance around some DC operating point. And so you can do that quite easily here. You just say, what's the derivative of this current here with respect to V1? That's the conductance. The VB is constant, right? And so, I mean, the easiest way to do it is just to write it out. After a while, you just do it automatically. You say in small signal, you say CV1 dot equals, it's the I is constant. We'll make I to be a small signal I, right? So let's say it's, there's only one conductance, which is the source conductance. So it's minus GS V1. Let's go small signal, right? When we write the V like this in this twiddly way, like that means small signal. That means around the DC. It's just the change from the DC operating point. So GS is the source conductance. There's no other conductance that matters here. Minus I. And it's a minus GS, right? So if V1 goes up, then the current through this top transistor decreases. That's why the conductance is negative. And GS, remember GS by definition here, GS is I over UT. That's the subthreshold source conductance. Okay, so that's the small signal equation. Shall we solve for the transfer function, small signal transfer function too? Frequency response. Okay, let's do that next. So I'll do that in red. So now what we do is we get rid of the dot. We say, we replace the derivative with respect to time with an S. First, let's put in a definition here that tau equals C over GS. That's the time constant. Okay, and then we can get rid of the dot here, and I'll do this, I guess, in, I don't know, some other color to make it clear. So now we have, when we do that, when we divide by C over by GS here, we get tau S plus 1, because we put it on the other side, V1 equals minus I divided by GS. So that's the S plane transfer function. And so now we can say that V1 divided by I over GS, the magnitude of that is the magnitude of 1 over tau S plus 1. So that tells you that it's basically just a low pass filter. So you see, this is the magnitude of the transfer function in the S plane representation. And what does it say about the DC gain at low frequency? It says that the DC gain is 1 at low frequency. What does that really mean, though, when we use proper dimensions for the voltage? Well, we already have proper dimensions because GS has a 1 over UT in it, right? Okay, so I hope that's clear.
Sorry, Professor.
I kind of doubt it because I think I went a bit fast here. So let me just plot it here as a function of frequency. So if we take omega equals JS, let me do this. S equals J omega. So we take complex frequency, just a sinusoidal frequency here, and on a log scale. And we plot the magnitude of H here. This is H. The magnitude of H. Then we get the classic low pass filter, right? Where it rolls off like 1 over with a slope of -1. And the cutoff frequency here is just 1 over tau in radians per second. Now, what was your question?
Just from above threshold electronics, why didn't, like, I would expect the conductance term to be in the transfer function. Why is it with I in the denominator for the
Oh,
The X
because
over
it's a
I.
transconductance circuit, right? So it doesn't really properly have a voltage gain because the input is current and the output is voltage. So it's really like a transconductance there's no, in a classic voltage amplifier, the gain is dimensionless, right? Because you put in volts and you get out volts. Here you put in current and you get out volts. So somehow the gain has to be defined in volts per change in current.
Okay.
Now, am I doing this wrong? Maybe I made a mistake here. Yeah, so possibly you're correct. In other words, let me put the proper units in here. I'm having to move this up a little bit. It's getting a bit crowded here. Let me try to do this. So GS, we already said that GS is I over UT, right? So if we write this out properly, I have a feeling I left out some units here. No, there's no units left out. This all has the proper units, this equation. So then really this expression here means the V1 divided by I divided by GS. GS is, what is it? I over UT, right? So it's divided by GS. So I divided by GS. Is that correct? Yeah, because I divided by GS to get the tau. Here. But if I divide the whole expression, this whole thing by GS, then you get the equation here. So I divided by GS, and GS is I divided by I over UT. I'm getting a bit mixed up here about this. So it's I divided by UT. Now I'm getting confused. It must be dimensionless. It must be V1 over UT divided by I divided by the big I. So this kind of makes sense. Now it's a dimensionless gain. In other words, this is the gain in thermovolts per fractional change in current. So little I is the small signal change in the current. Big I is the operating point. It's the whatever DC operating point you're working at. And so this is a small signal voltage gain in thermovolts per fractional change in current. Okay, so I have the circuit. I'm going to draw the circuit again in white here. So we start with a photodiode, as always, connected to ground. Then there's a feedback transistor, the drain of which is connected to VDD. Then we have the output node. We'll put a current, a transistor there. And then for the purpose of this, we'll put a PFET there, but for the purpose of this analysis, it'll just act like a current source. It'll be saturated all the time, and it'll just act like a current source IB. So we have a V1 node for this exercise, a V2 node. We're going to have a C1 here, which is the parasitic capacitance on the input. And on the output, we'll put a C2. Somebody ask a question there, or is that Skype? Oh, no, okay. And that's it. Do we have any other state variables? V1, C1, V2, C2. Oh yeah, there's one more important thing that we need to put here. I almost don't have room to draw it. But for the purpose of this analysis, we need to have some finite output conductance on this transistor, which I'm going to explicitly put in as a G2, I guess. And we'll label these guys M1, M2, and we don't need M3. So G2 is the drain conductance associated with M2. And so now it's very straightforward to just write out the differential equations governing these nodes. Once you do one of these things, you've done them all, basically. And we'll assume everything is sub-threshold, and we'll kind of try to be dimensionless as much as possible just to make it prettier. So we need to do the input node, right? So the V1 node. Well, first, let's compute the DC operating point, okay? Because that's important for any calculation. So it's maybe not obvious how this circuit works, but it's a very favorite exam question to ask you what are the operating voltages. So let me, for the purpose of doing that, I'm going to try to do something here. I'll make a copy of this. Sorry. And now let me just copy that. Put it over here somewhere. Cool. Okay, so now let's compute for this copy. What's the DC operating point? So, and for that, we actually need to replace this transistor with a PFET. So let's put in a PFET there and put a bias voltage on it. Just makes it easier to compute the voltages if we have a bias transistor there with a bias voltage on it, VB. That's some voltage VB away from VDD. It's a PFET, so we only care about the voltage, not relative to ground, but from VDD, right? And then if we want to calculate the actual voltage here at this node, we need to know what the photocurrent is. So for the purpose, since we already said that the photodiode acts like a current sink, let's replace this so we can actually compute the voltage. Let's replace this with a transistor. And you know that a transistor acts like a constant current source or constant current sink as long as it's in saturation. And by putting a transistor there, we can put a voltage on the gate of that transistor, V1 or V0. And now we have voltages, right? We don't have any currents to worry about. So let's reason about what V2 and V1 are. So first of all, for this circuit to work properly in its feedback way so that it holds the gate where it wants it, what should V1 be? V1 must turn on M2 enough that M2 sinks the VB current here, right? So we know that V1 must be about equal to VB, if VB is the voltage away from VDD. So right away, we can reason by this way that V1 is approximately equal to VB. I don't mean VB being like 3 volts. I mean, VB is like 0.7 volts. Say it's turned on by 0.7 volts. So V1 must be about, let's make it explicit. If VB is 0.7 volts from VDD, then what's V1? It must be about 0.7 volts from ground too, right? Because otherwise this transistor down here, M2, wouldn't be on the proper amount to sink the VB current. So now we know what V1 is. Okay, so V1 is 0.7. What about V2? What must V2 be? And let's be explicit here and set this input voltage here equal to 0.4 volts, right? So by this reasoning, what must V2 be? The V0 is 0.4 volts. Well, if V0 is 0.4 volts, this transistor M0 here is conducting 0.4 volts worth of current. So that must flow through M1 also, correct? So therefore, if we assume that kappa equals 1, we know that V2 minus V1, the VGS of M1 must also be about 0.4. So this voltage must be about 4 volts. And since V1 is 0.7, this must be about 1.1 volts by this reasoning. Everybody follow that? That's how you reason your way around approximately what are the DC voltages in a circuit like this. Okay.
Sorry, how do you come to the assumption that V0 is 0.4 volts?
I just assumed that it's turned on a little bit, you know.
Okay.
That's my input. That's the gate voltage that would make a current that's like the photocurrent.
All right.
I just assumed it. So you really have 2 inputs here, right? You have V0 and VB, and your job is to compute the other voltages. By the way, this is a very favorite type of exam question. We ask you to reason about the DC voltages in a circuit like this. And you'll see it just comes down to reasoning about the VGSs. Like, if you can't do this, you can't pass the exam, basically. You know, so you have to be able to do this kind of reasoning. Yeah.
Excuse me, can I ask you a question?
Yeah.
If we have a VO of 0.4 and the V1, what is the limit for V2? Because if V2 has a limit of 1.8, then V1 can't go over 1.4. can possibly go over 1.4. That case.
Go over 1 point. I don't know about the limits here. I'm not sure what you're talking about. You're assuming that you have a power supply voltage of 1.8 volts, say?
Mhm.
And then what? You're claiming that some limit. By the way, everything I'm assuming here is that every transistor is fully in saturation. In other words, it assumes that everything is working properly. It doesn't say what are the voltage limits. But for the circuit to work, the transistors must be in saturation.
Yes.
Everybody must be
I
in
was-
saturation. In other words, I need to have a big enough drain source voltage.
Okay.
So you practice, you can do other stuff like that. You can do it for a transconductance amplifier, wide range trans amp. I mean, let me tell you, if you want to be well prepared for the exam, this should be like effortless. Okay. And you make all the simplest possible assumptions. You always assume kappa equals 1, kappa n and kappa p are both 1, that I0 n equals I0 p, that W over L is all the same for all the transistors. I'm just telling you, just make it as simple as possible, but it's just about reasoning about these VGSs. Okay, so we're in agreement that, we can reason about the DC level. And by the same token, you should be able to compute from this circuit what is the DC output voltage of this circuit as a function of the photocurrent. Right? Because now if we have this photocurrent here, you should be able to write the equations of this circuit and be able to compute the DC output voltage. I'm not going to do that for you. I'll just directly write the differential equations. So let's write the differential equations for V1 and V2. Large signal means no transconductances here, just large signal differential equations. So how do we do that? So let's start with the V1 node, right? So we know that C1 V1 dot, that's the current flowing onto that capacitor. That's equal to what? Well, it's coming from M1, right? There's only two places. It comes from M1 and it gets sucked out by the photodiode. So it's basically E to the kappa V2 minus V1. That's the current through M1. And it's minus the photocurrent. That's the whole equation. That makes sense? What about the V2 node? So V2 node, C2, V2 dot. That gets a little bit trickier. Well, that's equal to the current flowing onto the capacitor is IB. That's a constant current. Minus the current flowing out through the transistor transconductance. That's minus E to the kappa. The source is at ground, e to the kappa V1. Now we need to put in the output conductance. So now the higher the voltage, the more is flowing off the capacitor. So it's minus G2 times V2. G2 is what I'm calling the drain conductance here of this bottom transistor. Anyway, that's the full differential equations, large signal. They're large signal because they have these exponentials in them, so they're not linear. But you can easily linearize them around some DC operating point and put in conductances instead of exponentials. But if you want to just simulate numerically this equation, you can just use these two differential equations. In fact, that's exactly what we have done for you in the exercise, but for the source follower. It's your job to put these equations into the exercise and do a large signal simulation of this circuit and compare it with the simulation of the source follower. Is that helpful? So do you want me to go on and do the small signal stuff too? And then I'll compute the transfer function in small signal as a function of the time constants. I think that's helpful exercise too, because you have to do some algebra. So let's now write it in terms of conductances. Basically, all you have to do is differentiate these things with respect to the voltages, because the conductance is changing current with respect to voltage. And so we can rewrite these equations. Should I change the color? Let's do a small signal in, I don't know, cyan. So then we have C1 V1 dot equals, we need the transconductance here. So we need to differentiate with respect to V2, right? First of all, with respect to V2. So it's let's see to the cap V2. It's just it's really like a GM, right? So it's a let me review how I did this. I did all this chicken scratching before. This one. Oh, that's the other one. I think it's this one. Yeah, these are the two equations. I'm going to do it for you because otherwise you won't be able to follow it just watching it here. Okay, let's go back to where I was. What happened to oh, wait a minute over there. Okay. Okay, you guys still with me? Okay, so now we need to differentiate this with respect to V2. That'll give us, and then that's really the transconductance of M1. So it's GM1. That's the gate transconductance times V2. I'm going to write with the twiddles to indicate small signal. So that's the transconductance of transistor M1 with V2 minus the GS1, that's the source conductance of this one, V1, and then minus the small signal current, I, little I. Remember, when you do small signal, you just subtract the DC part and just make a small change, little I around the DC part. And now if we do the same thing, C2, V2 dot, equals, we don't care about the IB, it's constant. It's minus, and now we're talking about the transconductance of M2. So it's GM2 V1 minus G, it's really GO2 V2. It's the output conductance of transistor 2. And so those are the complete small signal equations. Now, it may bother you that these GMs and so on don't have any real numbers on them, but you can compute all those numbers, right? Easily. Given that you know what the current is. And you know what the once you have the current, then you know what the transconductance is for subthreshold, right? Like what's GO2, for instance? Everybody know what that is? The output conductance of this M2 transistor. What is that? Assuming that it has an early voltage VE. Everybody knows that, right? If you don't, you're really behind, right? So GO2 is the output conductance. That's the current, the saturation current divided by the early voltage. So GO2 is IB. It's working at the current IB divided by its early voltage. That's clear, right? What about GM2? What's GM2? GM2, that's a subthreshold transconductance operating at a current of IB. So what's that? Come on, somebody tell me. You guys must know this.
Kappa IB over UT.
Yeah, thank you. Kappa IB over UT, and so on. We definitely expect you to be able to do these kind of calculations, okay? Okay, so now once you have these equations 1 and 2, you can now do some definitions which are nice to make it look prettier. For example, you can define some time constants. So I'm going to do that here. I'm going to define a tau1, which is an input time constant, a tau1 here, and an output time constant, tau2. That's kind of the RC time constant associated with that node. That makes it more intuitive for me. You don't have to do that, but it makes it prettier and easier to understand later, at least for me. And so I'm going to define, what's the natural definition of tau1? Let's define tau1 to be C1 divided by some conductance, but what should it be? Maybe GS. Tau1 is C1 divided by GS1. It's kind of the source conductance, what we had before. Okay, so that appears here and here, right? So that'll make that prettier. And now let's define tau2 to be the time constant of the output node. So what conductance should we use for that? Well, here it doesn't make sense to use a transconductance, right? Because there is no transconductance. It's like a voltage amplifier output. So the only conductance that matters is the output conductance, which is the drain conductance of M2. So tau2 will be defined as C2 divided by GO2. That'll be a much bigger time constant, right? Usually the output conductance is much smaller. Okay, so now if you define those, now you can rewrite these equations in a nice way as follows. So let's take 1 and write it like this. 1 will be tau1, and let's put the S in here, times V1. That's replacing the ddt by S. That's equal to GM1 divided by GS1 times V2 minus V1 minus I, the current divided by GS1. So current divided by conductance. So that's already kind of nice, because what do we know about this expression right here? What's GM1 divided by GS1? In other words, what's the ratio of transconductance to source conductance? It's just 1 over kappa, right? Okay. Okay, so then let's take 2 and do the same thing here. So then we have tau2 S V2, and that's from this first term. Now when we divide by GO2, so we already know that we're going to get plus V2. So I'll move the V2 over to the left immediately. So we have all the V2 on the left, and then we have minus GM2 divided by GO2 times V1. And that's by definition minus A times V1. Why is it A? Because remember, the voltage gain of such an amplifier is the ratio of transconductance to output conductance. The bigger the transconductance, the bigger the transconductance, the more the current changes with input voltage, and the bigger the output resistance, the more the output voltage changes when you change the current. So that's why it's a ratio. The voltage gain is a ratio of those two numbers. So now you have really simple form for these two equations. If I rewrite them, you'll see that they become quite simple small signal equations. So you have, I'll just rewrite it here. Again, I'm sorry about the mess. I'm not really bad at this. So we have tau1 S plus 1 V1 equals 1 over kappa V2 minus I over GS1. And then 2 becomes tau2S plus 1. You see, they both look like low-pass filters, right? V2 equals minus AV1. Okay, so that's makes it nice and easy, right, to understand. Now you just have two coupled polynomial equations. I mean, they're not even differential equations, right? This is two polynomial equations where they're kind of mixed together. Both of them look kind of like a low-pass filter, right? They look like a tau S plus 1 times something equals the other thing. But they're coupled together in that each equation has the other equation's variable. And so how do we solve for now the transfer function? We have to solve for V2 as a function of I, right? We don't care about V1 for the moment. We want the output voltage here as a function of the input current I. And so we have to do a little bit of algebra to solve that. Do you want me to do that algebra, or would you like to just see the result? We're running a bit short on time, but I'll just quickly do this algebra. I mean, it's almost trivial in a way. What we want is V2, right? And we have V1 here on the right, and we already have an equation for V1. It's simple. So we just put that in here. It's minus A times V1, right? A is, oh, well, it's 1 over kappa V2 minus I over GS. Can't even read my handwriting. Divided by tau 1s plus 1. Yeah, now we have an equation with V2 on both sides. So we had to put the V2 term on the right here. We had to put it on the left. And then we have the solution. We can isolate V2. If I do that, do you guys really want me to do this? Or can I show you the result? Okay, I'm just going to show you the result of doing this, a little bit of algebra here, which is in this thing I did yesterday. I believe it's here. So here's where I moved the stuff on the left, on the right, over to the left. Then next thing I did was I solved for V2 explicitly by putting all this stuff back on the right as a function, V2 as a function of I. When you do that, you find out that it's quite cool that this tau 1s cancels out, and you have in the end, you have that V2 is equal to minus A times I over GS. GS is this G that I had in the other equation. And then in the bottom is the product, tau 1s plus 1 times tau 2s plus 1 plus kappa times A. Okay. Now, if you expand out this product here, what you get in the bottom is tau 1 tau 2 s squared, that's these two terms, plus tau 1 plus tau 2 s, that's taking the two middle terms, plus 1, that's just the 1 times 1, plus kappa A. Okay, you could just immediately strike out the 1 here because it's much less than kappa A. You know A is much, much bigger than 1, right? So you just get rid of the 1, right? So cancel it. And then what you want is to get that 1 back in there. So divide by kappa A. So you divide the bottom and the top by kappa A. And now you can take the limit. You can ask the question, which is the only question I asked so far of this on paper, which is what happens when you make this amplifier here really, really fast? Then we should see that speed up that we predicted. Remember when I said that, when you have the feedback, it increases the conductance? What that should do is make this thing look like a first order low pass filter, but with a much shorter time constant. You do that if you take this equation and just set the limit that tau 2 goes to 0. Why is that saying that it's fast? Because if tau 2 is 0, it's basically saying that you really cranked up IB here. So it's a really big current. So you've made this C2 over GO2 really, really small compared to tau 1. So you really crank it up so it's like infinitely fast. It reacts instantly. Then if you do that and you look at the transfer function, what you see is that it reduces to a very simple form, which is shown on the right here. If the tau 2 goes to 0 here, so this term goes away. And this term goes away. And we're dividing by kappa A, right, everywhere on both sides, on top and bottom. And then you end up with the form shown right here. And you find out that finally V2 is proportional to the small signal current divided by the DC level of the current times UT. So it's the thermal voltage. And in the bottom, you have tau 1s, that's the input time constant, divided by kappa A plus 1. So this is a low pass filter, right? It's tau s plus 1 form. But the time constant here is not tau 1 anymore. It's tau 1 divided by kappa A. And what is kappa A? Kappa A is exactly the loop gain. It's really cool, actually. If you look at it, I'll just stop with this. But you see, it's actually the total loop gain, right? Because what's the gain going around this loop? This way, the gain is minus A, and this way, the gain is kappa. So if you multiply those two gains going all the way around, you get kappa times A. And so you get the speed up of exactly that factor, the loop gain. If you don't include the cascodes and stuff like that, which makes things a lot more complicated. So now that you have this transfer function, which is this polynomial form, this one here, maybe this is the most convenient to work with, because it isolates the two time constants. You can now do things like put in S equals J omega. You can put in real values for all these things. And now you can plot the magnitude of this transfer function as a function of the frequency. And you can solve for the roots of the denominator of this polynomial. And when you solve for the roots, what does that mean, solve for the roots? There would solve for the values of S that make the denominator 0. So if I solve for those values of S that make the denominator 0, then I find the natural responses of this circuit. Do you remember when we talked about that? That the roots of the denominator of the polynomial correspond to the natural responses of the system to a disturbance in the absence of driving it. Because only the natural response remains, right? That's the only thing that can happen to the circuit if you're not driving it. It can only respond with some exponential. That's either ringing or decaying or exploding. And so your exercise now is going to be split over. I'll talk about it again next week, but basically you solve for those roots. You can plot the root locus plot and you can understand the behavior of the circuit as you change, for example, the bias circuit, the bias current driving it. Okay, so I hope that's helpful. That's kind of an introduction to second order analysis of a circuit like this. It's the same thing you do for any such second order system. You'll find that it has much more richness than you might expect. You know, people spend long time trying to really grok this stuff and get intuition about it.